Welcome to the deep dive. If you're prepping for a meeting, exploring new tech, or just, really curious, we cut through the noise for you. We deliver the essential insights. Today, we are diving deep into modern 3D asset generation. Think high-end games, big film VFX pipelines, complex VR worlds, all that heavy lifting. And for years, the industry's wrestled with this basic trade-off, right? Speed versus geometric accuracy. If you try to generate a complex 3D model really fast, say, from just text or a single image, you usually sacrifice, well, usable quality.
Yeah, and the sources we looked at explain why that trade-off happens. Generating a full 3D shape from one 2D picture, researchers call that an ill-posed problem.
Aye.
You're just missing so much information, you don't have depth, you don't know what's hidden on the backside. Precise scale is often a guess.
Right, and that lack of info, that ambiguity, it shows up as distortion in the geometry. You get models that look flat or stretched weirdly, or they just miss key details. Basically, they're unusable without hours of manual cleanup, which costs a fortune.
Exactly. But what's really interesting now is this pivot point we're seeing. The industry's shifting. It's moving away from just relying on creative prompts, like text descriptions, and moving much more towards specific geometric guidance. Our source material today is all about Tencent's Hunyuan3D-Omni framework. And this system is designed precisely to bridge that accuracy gap. It lets creators feed the AI really specific structured blueprints for the geometry they actually want.
So that's the Omni part. Okay, that's our mission for this deep dive then. We're going to unpack this unified framework, explain how it handles 4 distinct conditioning signals, point cloud, voxel, bounding box, and skeleton, and how it combines them into one model to give creators this like fine-grained geometric control. We're shifting from asking the AI to, make a cool spaceship to telling it exactly where the landing gear should sit, for instance.
Right. And to really appreciate what they've done with Omni, we need a little context on the foundation it sits on. That's native 3D generation. This approach is crucial. It offers huge advantages in quality and speed compared to older methods. It basically uses 2 main components working together. First up is the 3D variational autoencoder, or VAE. Think of the VAE as like a necessary compression step. Its job is to take complex geometry, usually these point clouds sampled from a detailed mesh, and squash it down into a really efficient representation. It's called a vexet.
Okay, compression. Why is that so vital? Is it just too much data otherwise?
Exactly. If you try to feed the raw, massive data file of a 3D model into a diffusion model directly, the whole thing just grinds to a halt. It's too much. The vexet is essentially the model's geometric dictionary. It's this lightweight, organized structure that lets the system talk about complex shapes efficiently. Once you have that dictionary, the second piece kicks in, the generation engine itself.
And that would be the 3D latent diffusion model, the LDM. So this LDM builds on the vexet representation, often using stacks of these diffusion transformers or DITs.
Correct. For the listener, the main thing is the LDM is the engine learning the connection between, say, an image and the corresponding 3D shape in that vexet form. That's how it generates the 3D asset efficiently.
And you mentioned Hunyuan3D-Omni builds on their earlier work, right? Hunyuan 3D 2.1.
Yes, exactly. They leveraged that powerful foundation. But the really crucial step, the industry shift, is realizing that even the best foundation model needs external guidance for reliable geometry. If you want custom production-ready outputs, you absolutely have to integrate these specialized controllable generation techniques. And that's the whole point of the Omni framework.
Okay, let's get into those controls now, because this seems to be where the system really shines. You said 4 specific conditions, each solving a different common problem in 3D work. Let's start with the one for animation, the skeleton condition.
Right. This is all about pose control, primarily for characters. It tackles a huge pain point. Let's say you feed it an image of a character mid-jump, some dynamic pose. But for rigging an animation, you need that model in a standard T-pose or A-pose. The skeleton condition lets you do that. It generates the model in the specified pose.
Okay, wow. So the model basically separates the character's look and texture from the actual geometry of the pose itself. I can just imagine the time savings for animators there. That T-pose is baseline for production, not starting with a mangled mesh you have to fix. That's a huge win.
Absolutely. It ensures the final geometry aligns correctly with that target pose, no matter what the input image looked like. And the way it represents this, it uses the 3D coordinates of the starting points of the main bone's body and hands. It gives it a clean structural map to follow.
All right, moving on. Another common issue, the skinny geometry problem. We've all seen AI models where objects look okay from the front, but have like 0 depth. So that brings us to the bounding box condition.
Yeah, this one controls the aspect ratio, the proportions of the object in its canonical space, length, with height ratios, it directly tackles that overly thin geometry issue you mentioned, which is super common when you generate from flat 2D art or cartoons that just don't show thickness clearly.
Okay, but when I first heard about this, I did wonder, is the model just like stretching the object naively? Is it that simple?
That's a fair question, and the sources had a great example proving it's smarter than that. In one experiment, they used the bounding box control to make a sofa much longer. And the model didn't just stretch the existing sofa mesh, it actually generated new supporting legs under the middle section to keep it structurally sound.
Oh, interesting.
Yeah, it shows it's doing geometry-aware manipulation. It kind of understands the object's function, which is key for making robust assets, and the input is simple, just the coordinates of the 8 corners of the box you want.
Okay, so we've got pose sorted, proportions handled. But what about cases where the lighting is weird or the object is complex and you just can't tell how deep it is from the picture? That sounds like the job for the third condition, the point cloud condition.
Precisely. This is all about getting that raw spatial structure, the depth information. Point clouds, which you can get from depth maps or maybe simulated LiDAR scans, give the model crucial spatial info. This input helps the model really perceive the physical structure. It helps resolve that deep ambiguity inherent in single-view inputs. It's basically getting the X, Y, and Z positions for lots of points on the surface.
What really struck me here was the flexibility you mentioned about data quality. Are they only using perfect, clean point clouds?
No, far from it, and that's what's quite impressive. The model doesn't just handle complete perfect point clouds. It's designed to work with partial noisy and incomplete ones, too. The kind you'd actually get from, say, a phone's depth sensor or a consumer RGBD camera. Real-world data. And even that partial, messy data still acts as a strong cue. It significantly improves how well the scale aligns and how much detail it recovers. Even just 10% of the surface points is way better than nothing.
That makes total sense for practical use. Okay, last one. The voxel condition. We just talked about point clouds for structure. Why add voxels too? Aren't they similar?
They are related, yes. Point clouds are great for the overall shape, but voxels, which are represented by their center coordinates, provide these sparse geometric cues. They seem particularly helpful for recovering fine specific details and ensuring the geometry matches in those areas. Think of voxels like 3D pixels, defining small volumes. The sources showed examples like using voxels to get the perfectly flat surface of a shield right, or capturing the delicate curve of a bird's wing accurately, or even making sure the model reproduces a specific low-poly style, like for a stylized cup. It's about aligning those fine details with the sparse geometric guide you provide.
Okay, so 4 distinct, powerful control methods. Points, boxes, skeletons, voxels. Very different types of data.
This must have been a big engineering challenge, right? How do you integrate all that variety into one model efficiently? You mentioned they specifically wanted to avoid having, like, separate heads for each modality, which sounds clunky and slow.
Exactly, that was a key design goal. And the elegance is in their solution. The unified control encoder. The core idea, the brilliance of it, is that they found a way to unify all 4 conditions by representing them all as some kind of point cloud, whether it's the 8 corners of a bounding box, the centers of the voxel cues, or the skeleton joint points. It all gets treated, fundamentally, as a cloud of input points. This means they can be processed by a shared encoder architecture, much more efficient.
Wait a second. If you treat 8 specific bounding box points the same way as thousands of noisy LiDAR points, isn't there a risk of confusion? How does the model know if this point cloud is meant to add detail, like depth info, or change the shape, like setting a pose? Ah, that is the critical nuance. You've hit on it. They needed a way to prevent that exact confusion, so they introduced an extra mechanism, the task embedding function, or task M. This is kind of the secret sauce here. This function assigns a unique code and embedding to each type of control signal: skeleton, box, voxel, point cloud. It essentially tells the model the intention behind those points it's receiving. Is this a pose instruction? Or is it surface detail guidance? The task embedding clarifies that. Then, this intention embedding gets combined with the geometric features extracted from the points themselves. That combined feature gets concatenated with the image features, which, by the way, they extract using the really powerful Dyno V2 encoder for top visual understanding, and then it all goes into the main diffusion transformer.
Okay, so it's a layered system. Points provide geometry, task embedding provides intent, image features to provide the visual look.
Exactly. It allows the model to correctly interpret all that structured data and know whether to modify the pose or just enhance the surface detail based on the input.
Clever. And training a model that's juggling all these different tasks simultaneously, that sounds notoriously hard. How did they manage the training process?
They used a smart approach, a progressive, difficulty-aware sampling strategy.
Difficulty aware, meaning?
Well, they looked at their training data and realized some control signals, especially that precise skeletal pose stuff, were just less common in the dataset and harder for the model to learn compared to, say, basic point cloud guidance. So their training strategy was biased. It gave a higher sampling probability, more training focus, to tasks involving those harder signals. They basically forced the model to pay more attention to the tricky, less common data, while slightly downweighting the easier, more abundant signals during training.
Ah, okay, so it learns the hard stuff properly without being overwhelmed by the easy stuff.
Precisely. This kind of clever scheduling helps ensure robust fusion across all the modalities. It makes sure all four controls work effectively together in the final model without one type dominating the others.
So let's bring this back to the listener. If you're someone creating 3D assets today, what does this very structured, very robust approach actually mean for your workflow?
It really boils down to repeatability and reliability. The experiments showed clearly that these controls effectively tackle those big problems we started with. Geometry getting distorted, things looking flat, missing details, weird aspect ratios from just using an image. These controls mitigate all of that significantly. The whole system just dramatically increases the robustness you can expect in a production pipeline.
It sounds like replacing the sort of random generative guesswork with a much more guided, reproducible process.
That's a great way to put it. Now, it is important to note this framework really excels at creating that geometrically sound initial asset, the base shell. The sources do mention that these controlled assets are often then passed to a final refinement model. They mention Hunyuan 3D 2.5 for really fine-tuning surfaces, materials, those last details.
So it's part of a larger pipeline, but it solves the hard part, first getting usable geometry.
Exactly. Hunyuan 3D-Omni is that systematic, unified model that brings all this complex, fine-grained control under one roof. That's the core benefit.
This definitely feels like a big step, moving generative AI from just being a fun concept tool towards being a genuine automated modeling tool, something that allows dynamic interaction, precise customization, taking the guesswork out of that initial 3D build.
Absolutely. And that functionality, that robustness brings us to a final thought. We talked about how the framework was deliberately designed to handle partial and noisy data, right? Like those simulated LiDAR scans. Because even that incomplete, kind of messy real-world data turned out to be a really strong signal for improving the geometry.
Right. So if even incomplete real-world data drastically improves the quality and alignment of today's 3D generation, it makes you wonder, doesn't it? What will the next generation of 3D models look like? Imagine training them not just on static images and clean lab datasets, but on constant streams of noisy, multimodal, real-time data from sensors embedded everywhere around us. The future of automated modeling might actually depend on embracing and learning from the inherent messiness of the real world, something to think about until our next deep dive.